going into the electromagnetic energy part, I'll talk a little bit about the basics of energy. So as we know that interest on the subject of energy is kind of ingrained in the thought process of humankind, and it has motivated this unprecedented evolution or revolution, how you may like to put it, in the world of science and technology. And the second sentence that I put here is probably true from philosophical sense as well, apart from the technical sense, that in the history of human civilization, the quest for acquiring and controlling energy or power has proved to be beneficial as well as destructive in various instances. Now, without going too much philosophical, in physics terms, energy is basically the capacity for doing work, which comes in various forms like chemical, thermal, electromagnetic, nuclear, gravitational, etc. So I just put some of the figures over here where like a matchstick where the chemical energy is being converted into thermal energy, and then here also this electric induction oven kind of thing where it is heating up the water. So now other forms of energy are also there. So if we try to classify this energy in terms of commercial terms, so from the context of commercial application, the source of energy can be classified into groups. One can be this renewable and one is the non-renewable. So non-renewable are the ones as I am showing in the right column here, that starting from this coal and then oil and natural gas, then we have hydrocarbon and all these things. So these are basically fossil fuel based, and nuclear energy is also there. So kind of non-renewable energy we can say. But renewable energy, again, we have this, as you can see from this infographic, that you have the solar, then you have the water or this hydropower based energies over there, waves. So this is related to the hydropower part. Then we have the wind energy and we have the biomass, all these kind of things are there. So this is a classification from a commercial perspective. Now, if we say from a physics point of view, then we can again reorder these different sets of energy into potential energy and kinetic energy. So potential energy, we mean that the energy that is stored in the chemical bonds, or it holds the nucleus together, or stays in the springs. And kinetic energy is something that is associated with the motion of waves, electrons, atoms, or molecules, and it is manifested in the sound, electromagnetic radiation, or heat. Dr. Shukomol, can you mute the participant where the mic is still on? Yeah, I think it's okay now. So you can see that energy of this kinetic and the potential, these can be interchanged and intertransformed, you can say, in various ways. One of the examples is shown in the figure, where the kinetic energy is transformed into potential energy, and again it is being transferred into the kinetic energy. So these are all stuff that we know from the knowledge of our basic physics. Now, when we talk about electromagnetic energy, among these various other forms that I have mentioned, harnessing and processing of the energy linked to the electromagnetic waves has proved to be instrumental for various applications. And especially since we are talking about the wireless communication aspect, wireless communication revolution from first generation to fifth generation and beyond that has taken place in the past century, this electromagnetic energy is extremely important. So EM radiation, as we often say in abridged form, it is associated with the vast spectrum of radio waves, infrared, visible light, ultraviolet, X-ray, gamma rays, etc. But in relevance to the wireless communication, we generally focus on the radio waves in the ultra-high frequency, microwave, millimeter wave, sub-terahertz frequency range. So just this infographic, you can see that starting from this X-rays to this UV, and in between we have the visible part, and infrared is there, microwave is there. So as we are increasing in terms of the wavelength or decreasing in terms of the frequency. So we are generally we talk about this microwave frequency range, and most of the research that I will be stating here is formulated in the microwave frequency range. But the concepts that I will be introducing can be extended to the regions where the classical model or classical mechanism of this electromagnetic energy formulation is still valid. So all those situations, the theory that I will be presenting will be applicable. Now, since I talked a little bit about the renewable energy, and one of the important like facets of this research is the focus or the stress towards the green energy. Like we talk about solar energy and solar cells and stuff like that. But apart from that, another very popular avenue that is coming up, or some of the research has been done over the past few years, is mostly the RF energy harvesting. And you can see the network that I am showing here, that there is this electromagnetic radiation that is incident on the antenna. And then finally, we want to get some kind of DC a power that is dissipated across a DC load, and that can maybe charge your battery or small implanted, wireless implanted devices. So one of the key research part is the design of this matching network and the design of the rectifier. So this is the main challenge in this kind of RF energy harvesting problem. And since in the recent years, there is a huge proliferation of this RF or mobile communication in a developing country like India. So that is why this RF energy harvesting is becoming an attractive solution, so that the dramatically increasing energy needs can be satisfied. So why I mentioned this point is that the ultimate application of this kind of research, or more fundamental research on the electromagnetic energy, is pointing towards developing systems for RF energy harvesting and wireless power transfer. I have not put a slide on that, but wireless power transfer applications, that is also another application area. But the point is, while going to the application part, we also need to look back into the theoretical aspects or the more fundamental aspects, because if you understand those things, like for example here, if you understand the energy distribution around the antennas correctly, then that will help you to build better networks for matching and the other backend networks. Or maybe we can tune the antenna geometry in the most optimal way, such that it can process the electromagnetic radiation. Another part is that the electromagnetic radiation here is mostly this model, or the diagram that I am showing is from a plane wave perspective. But it could be that some of the sources are not in the far field region. So the wave that will be interacting with the antenna will be acting in the near field. So all these kind of things and all these kind of research areas come up. And for that, we need to look back or make some insight into the energy distribution around the antennas. So the importance I will be stressing on with a few more slides, that as we are talking about the 5G technology that has the data rate of 10 Gbps order and very low latency, and also we are talking about the Internet of Things, like enhanced mobile broadband, as well as the large Internet of Things, where many antennas are going to be packed in a small space. So in this kind of scenario, what happens to the near field electromagnetic energy distribution and exchange between these multiple antennas? Because we know from our knowledge of wireless communication that we need to go for MIMO solution when we go for the 4G to 5G kind of things. So we need to have multiple antennas. And also there are multifunctional antennas, like we have the antennas for Bluetooth, we have it for GPS, Wi-Fi, and other near field communication system. So there are multiple antennas packed into a single device. So this is just one representative figure that I have taken from the IEEE Spectrum, November 2018, where you can see, probably the font is very small, so I can read it out for you, that we have Wi-Fi antenna, we have 5G antenna, we have the other diversity antennas corresponding to the 5G. And then the normal cellular communication, we have this low to mid-band and carrier aggregation kind of systems over there. And also there is this near field communication antenna, RFID kind of stuff. And if you look into an Apple Watch or any other kind of this kind of smartwatch kind of things, we have Wi-Fi, Bluetooth, and GPS, and also the LTE cellular antennas also. So the point that I'm again trying to emphasize upon is, we will be having multiple antennas packed within a small space, and we can no longer run away to the far field to predict the electromagnetic energy. We have to think about the near field energy in a holistic way. And this is also not only from the handset or the device perspective, this is also important when we talk about these massive MIMO antennas and where we can probably keep, to reduce the base station form factor, we can probably keep the number of antennas very closely packed together. So how can we look into such optimal arrangement of antennas so that we can have less mutual coupling and lesser energy localization, or maybe we want to localize our energy or confine our energy into certain directions. So all these kind of things we have to look into. So this points towards this near field electromagnetic energy distribution as well. There is also another application that is very popular, and some of the groups in Italy are working on this, groups by Paolo Nepa and Professor Manara, that these near field focused arrays, and where we can use this kind of antennas to get a near field focusing. Like, it's not the conventional far field focusing. We are trying to predict or localize, or we are trying to increase the gain in a near field range. So there, the wave modeling or the propagation modeling will not be handling this plane wave kind of a scenario. We have to look into the spherical wavefront, and all kinds of stuff can emerge from there. But again, the point is that importance of near field. Now, if you go into the optical domain, because I so far talked about the like microwave part, but if you go into the optical domain, then you'll see that this near field energy localization or near field field strength kind of things, these are observed in this enhanced light focusing and local temperature control, and also the localized light matter interaction with optical antennas. So the importance of localized energy or the field localization, these are already addressed, or these are somehow, like I can say that these are addressed more in the optical frequency ranges. But when we talk about the microwave or in the RF antenna domain, sometimes our viewpoint is not this like broad. So I'll come into that, why I'm saying this kind of stuff. But before going to that, just to place the context of our research in this context, that we have the electromagnetics in wireless system analyzed it from various points of view. So I work on the channel modeling and all this kind of stuff, spatial correlation analysis. But I'll be not talking about on that. This talk is mostly concentrated about this general near field aspects of antennas. So that thing which I built up so far. So energy around antennas, when we talk from a conventional perspective, we talk about this reactive energy more often, like people who have done any basic antenna course or circuit course also, that they can understand the concept of this reactive energy. Sometimes we call it stored energy in an inductor, stored energy in a capacitor kind of thing we talk about. So it is basically the reactive energy. But now when we try to define another new term, which is the localized energy. Now the questions may arise that why do we need this new term? We are doing fine with this reactive energy. So why we need a new definition? So that is why I'll be explaining next. But before going into that, I'll be talking about this reconsiderations, or why we need this reconsideration from the reactive energy point. So one key parameter that we generally use while looking into this reactive energy thing is the antenna Q factor. We define the radiation Q factor by twice pi, the ratio of the reactive energy to the energy radiated per cycle. And where you can see the mathematics, that where this omega naught is the twice pi into F naught. F naught is the excitation frequency. This W tilde is representing the total reactive energy, and the tilde is representing the total radiated power. Now we identified some of the issues that are there with this Q factor, because this model is very much useful for engineers who are working with electrically small antennas and dealing with this impedance matching problems. But our point was that this is not the most general way to look into the energy around antenna, because Q factor, as you can see from the definition itself, it is relevant at a single frequency, especially for a resonant antenna. However, there are a wide class of non-resonant antennas also, which are some of them are leaky wave antennas. So there, the near field energy is still not explored to the extent it is done for the small antennas. But for those non-resonant antennas, we cannot simply put the Q factors to model the reactive energy. Also, Q factors are limited to the frequency domain analysis only, and it assumes the time harmonic excitation. This is also an obvious thing when we look into the definition itself, that it is relevant at a particular excitation frequency. But what about the antennas which are not excited by perpetual sinusoidal signal? Because in fact, you can say that this is valid for any antenna, because there is a starting time, there is a stop time, and also there is this pulsed excitation part. So here I have mentioned the pulse excitation, but the ultra wideband antenna, it is we can still excite it by say differentiated Gaussian, fourth order differentiated, fifth order differentiated for some application. So there you cannot use this particular definition to predict the near field energy distribution. So you have to go or find out some other mechanism where we can actually see the space-time variation of the near field energy for this kind of ultra wideband antennas. So next point, the point that I already mentioned, is all antenna excitation signals must start at some point and stop at some point. So the transient effects will be there. So when we talk about this kind of transient effects, we can no longer use the Q factor model, because the Q factor model inherently assumes that there is this steady state signal. So Dr. Sukomal, am I audible?
Yes, sir. You are audible.
Yeah. Okay. Sure. So, so the transient effects you cannot model using the Q factor. So again, I am reiterating the point that we need some new ways to look into the energy. So beyond the circuit models, like antennas are not just resonant circuits. So this is the figure that I have taken from a Balani's book, and you can probably recognize it, the people who have studied from this, that the transmit mode and the receive mode, there are various circuit models. So I'm not saying that the circuit models are wrong or anything. They are useful for the applications that they are designed for. But the point is, they have some kind of applications and they might not be most general. So our objective is to just say that there is a requirement for exploring more, because the antennas, the directional aspect of the antennas, antenna radiation, is missed from the equivalent circuit modeling for obvious reason. Like from this circuit, you cannot say which way your antenna is radiating. And the two antennas that bear the similar input impedance profile may be a different far field radiation pattern. So they can also have different near field energy distribution and the dynamics. So this is a very critical point, which we often try to model an antenna. Like the things that I have experienced is people sometimes simply get the S11 plot or model the input impedance plot and straight away try to report their antenna. But antenna is just not a simple reflection coefficient kind of thing. You have to look into the radiation pattern, and that is not captured while you model the antenna in terms of an equivalent circuit like this. So you have to know how the current distribution profile is on your system, whether it's a conducting antenna or whether it is a directly resonated antenna, anything. You need to understand the current distribution. You have to model it in terms of any discretized manner, like it can be using the finite element method or method of moments, or even FDTD. From that, you can get your radiation pattern plots. So we need to focus some things beyond the circuit models for the reactive energy, for this near field energy of antennas. So this argument we tried to put in this new consideration of the electromagnetic energy in antenna near field by time domain approach, which we reported 3 years back in 2017 in one of the AEMC conferences. So we pointed out some new directions at that time in 2017, that we need to find out the time domain or time evolution of the total reactive energy within a given volume circumscribing the antenna. So this was mostly pointing towards the fact that we defined the Q factor for a steady state kind of system. So we need to address the pulse excitation. We need to address the transient effect. So that is why one of the key research direction we pointed out at that time was time evolution of the total reactive energy. Then we tried to find out some of the things like this visualization of this localized energy distribution around any given antenna. So we wanted to go beyond the time evolution part. We wanted to see that how the energy is actually distributed across the antennas. And then we wanted to find out if there any connection between the localized energy distribution and the radiated energy distribution. Also, whether there is any energy exchange between the non-propagating and propagating antenna modes in time domain. So we thought that this will be, we can probably get some valuable design curves for the antenna engineers dealing with the gain enhancement and beam shaping, and we can devise some means to recover and utilize this reactive energy. So this is again the pointing towards the harvesting part. But this paper at that point, when we said all this kind of stuff, was met with some resistance, but we tried to work our way through it. And this magazine article that we will be publishing, that we have actually already, it is in the early access, but it will get officially published next year. So there we also pointed out some of the additional arguments, you can say, in favor of the requirement of something going beyond this Q factor. So what I tried to say here is there is, if you interested people can see this article, that one can find out the Q factor from the distribution or frequency function of the input impedance of the antenna in a certain way. Like if the input resistance and reactance are modeled like this, we can model the QZ, like the Q that is obtained from the Z, that is the input impedance of the antenna, using this mathematical relation. And if we are going into the high Q regime, then we can approximate this thing. But high Q regime means we are going into these electrically small antennas, which are mostly can have this negative realized gain kind of thing, that is very low radiation efficiency. That is the separate thing. But if we talk about in general, practical antennas do not always manifest a clear single pole behavior. So this undermines the basic assumption of a reciprocal relation between the Q and the band. So we always talk about a reciprocal relation between the Q factor and the bandwidth, but that is valid, or if you go or if you analyze the theory in details, that is related to this single pole behavior, and we operate near that kind of pole. And there are certain discrepancy between the half power bandwidth, the exact Q factor, and the parameter QZ, which raises the questions regarding the utility of the quantities Q and QZ in assessing the performance of a multi-resonance antenna. Because in present day, we are talking about this multi-band antenna or a wideband antenna, then there are definitely a problem if we simply rely on the QZ kind of formula to look into the Q factors. So we thought that there is need for this robust time domain approaches, and we tried to, we dug the literature a little bit, and we tried to see that whether people have used the time domain approaches like FDTD to model the energy around the antennas. So indeed they did, and I have cited those papers here, groups by Kolade, Sharaya, and Majdubi. They are having this evaluation of the antenna radiation Q using the FDTD method. But again, you can see from the title itself that although they are using a time domain tool, eventually they are focusing on the frequency domain Q factor. So some of the parts like the near field energy behavior for a multi-band or wideband antennas in transient excitation or the switching effect kind of thing was not there. So we dug up more and we saw that there are some analytical expressions that people do, radiators in time domain. These are papers by the Van den Bock and also Kapek and Jelinek, and there are groups like Gustafsson who are working on this. So a large amount of people in the Europe, they are working on this energy business. But the point is the approach or the formula that they have used or they have proposed in modeling the time domain currents and getting analytically the stored energy, they often say the stored energy term. So that is not always valid for real antenna system, because practical antenna systems, as I reiterate, multi-band, wideband, printed dipoles, monopoles or slots, the electric resonator antennas, liquid wave antennas, they do not always have well-defined analytical current distribution in space-time. So what we thought was the best way to get is to get a time domain infinitesimal dipole model for any arbitrary antenna that is decomposed in times of the FDTD grid. So that is the most direct way of obtaining the time domain antenna currents. So I'll again just try to explain the part that we want to see the behavior of the near field antenna energy for short pulse excitation, as well as we want to see that for the transient effects also. That is also another point of interest. So not only the steady state behavior, we want to see the time domain behavior as well. So the approach that we will be taking is we want to model the time domain antenna currents and get the time domain infinitesimal dipole model of it. And from that, somehow we have to find out the reactive energy and time. So that we actually addressed in this transaction paper, which was published in February 2019. We took a route through the time domain magnetic vector potential. So we know that for any current distribution, so if we have the current distribution modeled by this J, we can find out this magnetic vector potential in space and in time using this particular formula. And it is very well known. It is like this particular one I have taken from Griffith. And but like using different other maybe nomenclature, the same version of the formula is available in other books also. So the point is, if we sample this current somehow in terms of these small infinitesimal dipoles, which have a certain dipole moment, which is given by this Pn, and which have magnitude of the current and certain time variation. So this S of t that you can see is basically the time function that is applied on the excitation signal of each of these infinitesimal dipoles. So that we can basically contribution of that infinitesimal dipole to this complete time domain magnetic vector potential can be obtained by using this particular formula. So the next, once we get the contribution for each of these small dipoles on the time domain magnetic vector potential, then from that we can calculate the electric field. And once we get the electric field, we can get the time domain radiated power. So you can just have a brief look on the route that we have got this magnetic vector potential for the nth dipole, and from that we can calculate the radiated field that is due to this nth infinitesimal dipole, and we can sum it up eventually, because it in the far field, when we are trying to evaluate the far zone radiated power, we can very well apply the superposition theorem and we get the EIDM. And once we have the EIDM, then we can get this particular function, which is a time function of this radiation intensity, and then we can integrate it over the spherical coordinates to get the radiated power in time domain. So the catch here is in this term, that we all know that this is a concept of the retarded vector potential. So this TD has to be evaluated in a sensible way. So if you go through our paper, I will not go into the details over here, but there is a way to find out the TD for a given FDTD simulation volume. So we are modeling our antenna in a FDTD paradigm. So then from that we can get an efficient way to model this TD to match the variation or how the energy is escaping that FDTD box and it is radiated into the far zone domain. So that we can do. So once we are done, then we have a kind of time domain expression for this radiated power, which is valid for all types of temporal excitation of the antenna. This is important because you may see that, okay, this is known, but we have to regularize it for all types of antenna excitation. And the second point is, we can, from the FDTD simulation, we can actually evaluate this total electromagnetic energy density at each of the points by using the interpolated fields. So that part WEM is there, and then we differentiate it with respect to time to get a kind of time domain variation of this or slope that is for this total electromagnetic energy variation. And from that we devised this reactive energy formula. So this is the regularized reactive energy formula that is valid for any kind of temporal excitation, and arbitrary antenna geometry also, which can be actually, the arbitrary antenna geometry part is dependent on the FDTD tool that we are using. So how we discretize it, whether we are using simple cubical or parallelepiped kind of grids, or we are using some conformal FDTD, that is the point of how arbitrary a shape can we model accurately. But if we are actually interested into knowing the time domain variation, then that part is sorted out. So we used a simple FDTD grid, and we started off with a conventional dipole. and tried to see that whether now we can see the big picture, that we are trying to excite a dipole antenna very close to its impedance matching point. That here you can see that the impedance match point is roughly lying at this 2.58 gigahertz, and we put a signal of a frequency like this, 2.73 gigahertz. This is our F input, and from that, like this is our signal that is fed into the dipole. It is having a certain start point and it is having a certain stop point. So now you can see how the radiated power is built up, and it is basically in the steady state. And if you notice closely, that you can see that this is in the double frequency as expected, and the reactive energy distribution is also there. So here you do not see any kind of prominent transient effects, because, well, we are feeding the antenna roughly where it is supposed to capture the input power and radiate it out in the free space. So it is a kind of smooth going. When the switch is on, it takes some time to build up, but that time scale, you can see that it is of the order of some nanosecond. So this is very small when we talk about the practical application part. But the point is that there is a gradual build up and then a gradual decay kind of thing that is. But when we try to feed the antenna at a frequency that is way below the actual operating point, so we are feeding it, suppose, a 1 gigahertz signal. So effectively, this is a short dipole at that particular frequency. If you calculate the lambda, and you see that how much the fraction of lambda the dipole, it is no longer behaving, it will no longer be a half wavelength dipole. The same physical structure that will behave as a short dipole. And in that case, you can see that what happens when we just switch in the signal, at the initially the antenna will try to radiate at its fundamental frequency. So it will see that, okay, some disturbance is coming, and it will try to radiate it out in the fundamental frequency. But slowly it will realize that it is being fed with a 1 gigahertz signal, and it is achieving the steady state at that, for that 1 gigahertz part. And now if you compare the previous two plots, then the reactive energy has increased a great deal, and there is a certain variation of the reactive energy as well. So this study was very much important to see the transient effects, as you can see here, and also to get back the Q factor, because when we proposed this algorithm, it was obvious that the reviewers should ask, or the people who are going studying, that whether it is basically giving us the correct picture, or whether you can get back the Q factor for the dipole antenna from your tool. So we just had to do that, and we satisfied it. And it is quite obvious, but because it is the most general tool. But the point is, you can we use the reference data from the very well-known paper that gives the Q factor variation of the dipole with respect to this Ka term, and we found considerable match using our FDTD IDM algorithm. But our objective was not to look into the Q factor. We just did that for the benchmarking purpose. We wanted to study this multi-band dipole that has this multi-frequency kind of behavior, and we can see that we can basically tilt or basically tweak the structure of this single half wavelength dipole by loading it with certain lumped elements or lumped resonator kind of things, and we can actually get the multiple frequency impedance match over here. Just you can see the tri-band response that we are obtained, and then for the same dipole we fed with same time domain excitation signal. So this same differentiated Gaussian pulse excitation is taken in all the cases. And now you can clearly see that when we load the dipole with various of these resonators, there is a stark contrast in terms of the reactive energy plot, in terms of the radiated power plot in time domain. So you can see that there is this ringing kind of effect, and also there are certain interesting observations, like the way it peaks. It basically indicates the difference frequency between this multi-resonance, because these are not harmonic kind of thing. These are just used impedance matches are obtained by use of these lumped elements. So the ratio of the frequencies is not anything like, it is not a third order harmonic or something like that. So the difference frequency that also carries certain information and may be used in certain applications. So these observations we found from our algorithm. And then from a single antenna system, we extended the work into a multiple antenna system and obtained similar results. But now, so far, what we did was we focused on this time part. So this was another article that was followed after this transaction. It was an invited article in a issue in this RFCAD journal. So there we again stressed upon the importance that the time domain part is solved, but we need to look into the space domain, or the spatial distribution of the energy around the antennas in a more focused way, because the reactive energy model or the algorithm that we develop is basically averaging out the spatial distribution part. So if we want to probe more into the regions near the antenna, we have to go into we have to devise some other mechanism. So there we actually brought some of the arguments given by Feynman himself, where he states that the way we see the Poynting vector, or we study the Poynting vector in classroom and we model the energy conservation law, that there is infinite number of different possibilities to model the total energy around the antenna and the Poynting vector. So what we use is basically just one thought of an experimental way to tell. So there is no particular experimental way to say that which one is right. You can take various routes which have to be physically consistent, but the simplest one is most probably the correct one, but we cannot say that that is the only one. So it's kind of again, you can go into some philosophical domain from that. But the point was that we can define the energy around an antennas from other perspectives as well. So this was the point that we tried to make. So then we introduced this part. Like this one was reported by Said last year, probably around this February, March, sometime like that, on this localized energy. And this year, the complete work has been published on this new energy definition that we introduced, this Poynting localized energy, and it is in the transactions. So for that, the definition, before going into the formal definition, I would like to point out that generally we see the paper by Koo and Colin as the earlier papers on this subject of EM energy around antennas. But while doing this research, we had the interaction with Professor Ed Quester, who is a professor emeritus in the Department of Electrical, Computer and Energy Engineering in the University of Colorado Boulder. So he was very kind enough to share with us this very old Russian article, and you can see that it was published in 1939, and he translated the paper for us. And from there, we could see that there are certain concepts which are not exactly conforming to the reactive energy that we define, but it is something called bound energy, and it was defined around the radiating wires, and this was the formalism that was done. So that actually helped us to build more into another definition that we will be using. So the energy density, Poynting localized energy density, we define it in terms of the U minus 1 upon Vg modulus of this S. So S is our Poynting vector. So basically, we want to now, instead of going into the far zone radiated power, we are now concentrating on the Poynting vector, and Poynting vector at any point around the antenna. So it can be in the near field, it can go into the far field. So when it goes into the far field, it becomes similar to the radiation power density. But when it comes to the near field, it is no longer equal to the radiated power density, because in the near zone, you do not have the ratio of the electric and magnetic fields same as the intrinsic impedance of the medium. So there are certain caveats in that. So, and energy transport velocity, that is not also equal to the group velocity when we talk about in the near field. So there will be certain difference in between them, and that can be mapped in this particular definition. So when we look into this definition, that we get the total EM energy density in the similar way, but instead of using the far zone radiated power or anything like that, we use the localized Poynting vector. And we could then, for any formal definition, we had to prove that it is a positive semi-definite quantity, and then we had to satisfy the energy regularity. So these were some of the issues that were taken care by Said in his paper in Pierre. And then from that application part, that we can now again look into something like a spatially averaged Poynting localized energy, which is defined by this particular term, and we can compare it, whether it is same as the reactive energy or whether it is something less. So by intuition, we could sense that it will be less, and eventually from the numerical experiments also it came out like that, because when we are calculating the reactive energy, we are subtracting the far zone radiated power, which is from the total thing, we are subtracting something that is actually less. So the overall quantity that becomes more, that is the reactive energy over here. But when we are subtracting the near zone Poynting vector magnitude, then it is also having some of the other terms as well. So that actually brings the Poynting localized energy part down. Eventually the behavior of them will be same, and we can also maybe, if you want to define the Q factor from this Poynting localized energy, we can possibly go into the some kind of scaling kind of thing, and we can get back the reactive energy plot. Something can be done about that. But again, I reiterated that we did not want to go into the Q factor direction. So we, instead of the time domain kind of thing, we investigated the spatial part a little bit more. So from the reactive energy, we could not get this kind of spatial plots, because now we have a Poynting localized energy density defined, and now we can integrate it in the time domain like this. So instead of this dx, dy, dz, we are now going into the dt, and we are integrating it from the 0 to t max, where the t max is the maximum time that we are taking for our FDTD simulation. And this particular plot that I have given here is for a simple Yagi-Uda kind of configuration, where we have a driven element, we have a reflector, and we have a director. And now you can see how the Poynting localized energy around a single dipole looks like. This is along this xy plane, and if you look from the xz or other planes, then you can probably see this kind of other kind of plots. But if you, let's say, concentrate on this particular xy plane distribution, then you can see that when we put the reflector and when we put the director, how the energy is actually behaving near them. If you go away from the antenna, there is obviously no energy localization, because when you are going away from it, it is mostly coming into the far field, or at least the radiating near field. So, but when we try to see how the energy is near that, then we can further zoom into the plot, and we can probably point out finer spatial details. Similar operation was done on the pattern reconfigurable dipoles as well in another paper. So yeah, this plot is probably would be more clear. So this is another standard example taken by from the Balani's book, and this will be there in our magazine paper. So now you can see that how this exciter element and these 4 directors that I have put and the reflectors that I have used, how the energy is actually distributed between them. So this is very important in the sense that we can now find out some coupling paths between these near zone directors. Whenever we try to model this kind of coupled antenna system, we go into the circuit model. But if you want to look into from the field model perspective, then you can clearly see how the near field localized energy signature is behaving. And similar operation we did for these meta-resonator loaded antennas, where we use this split ring resonator and then array to basically tilt the beam or shape the beam in certain direction, enhance the beam radiation gain in certain direction, mostly in the infrared direction, as you can see. So they are also, the basic principle remains the same. You need to model the array of the resonators, and we have the exciter element, we have the reflector element, and you can notice the energy exchange between these various elements and how they are spatially located. So with the reactive energy or Q factor viewpoint, you cannot get this kind of plots. And same thing we did for the arrays also. Same concept was extended for weakly coupled arrays. Now the point that you can say that, okay, now we have the spatial features with us, but how does that help an antenna engineer, or what is the advantage, or what is the new thing or quick information that might not be obtained from a conventional point of view, or whether your point of view can like give you a certain alternative viewpoint to certain physical phenomena. So that we observe for that when in this paper actually it is mentioned in detail. So I'll just briefly summarize that point, that when we can have a very simple route to predict the gain enhancement in case of these strongly coupled antenna systems, like for example this Yagi-Uda. So when we try to predict the gain that will be enhanced by various director length and their spacing, this is just as one configuration, but we can tweak with the spacing between the directors, we can tweak with the number of director elements that is there, and we can use various other method of moment codes to solve for the currents and to get the gain that will be gain enhancement that can be done. So that is there. But we can now have an alternative approach, and that is very quick, and it will simply need 2 iterations of simulation, one from the reference system to the next antenna system. We can excite both the system with the same temporal pulse. It can be mostly the best thing that we can use is modulated Gaussian pulse at the desired frequency of interest, but we can also use other differentiated Gaussian pulse as well to just simply observe the phenomena that when we have, say, isolated exciter element and excited by this Gaussian pulse, then the localized energy behaves in certain way. This blue curve is representing that. But when we put this number of directors and the reflector element, the behavior changes. And basically, you can see a kind of stronger or enhanced response in terms of the localized energy. So this is physically obvious that since we are putting in more number of directors and reflectors, we have certain increase in the energy around the antenna, stored energy or non-propagating energy around the antenna. But if we define this particular metric, that is a factor that how much this enhancement is, so we can define it by further integrating the energy with respect to time. So you can say that it's action or something like that, I don't know. But from engineering point of view, our purpose is solved, that we can now have this kind of, evaluate this kind of ratio. And what we observed is this ratio comes out to be exactly equal to the gain enhancement that you can predict from other full wave solvers at the frequency. So simply by getting these 2 time domain energy plots, you can now evaluate the gain or how much the enhancement in the gain in the system is done. So this is one engineering application, and we are still like looking into that and regularizing it for other kind of elements. But the main thing is this kind of phenomena we could observe in a strongly coupled antenna system. So that we addressed in this transaction paper. Interested readers can go into that whether it is valid for weakly coupled system, let's say array that is spaced by lambda by 2 or something like that, probably there it will not be valid. But if you use a strongly coupled antenna system or parasitically excited antenna system, there this definition is valid. So this gives us an alternative picture. Another thing that has like perplexed the antenna researchers for quite some time is regarding the mutual coupling and whether we can predict the mutual coupling paths between the various elements. So Feynman also hinted about this in his book on the this electromagnetic energy part. So now the definition for the Q factor is not that formally used for multi-antenna systems, but this localized energy from the definition itself, you can easily apply it into any number of antenna elements. So here I have taken a 2-element system, and also I have not chosen any narrowband radiator. This is basically ultra wideband radiator and very well known this fat half elliptic or half circular kind of dipoles. And if you place them close together, this will give you to a 2-element kind of system. So one case I have kept the ground planes disconnected, and here I have kept the ground planes connected. So this is entirely in the free space, and we basically excite these 2 antenna systems at the center. In the simulation, it is done by a simple delta gap kind of excitation, but for practical thing, it can be done by any connector. So the point is that when we compare these 2 systems, we get through the VSWR, and we also look into the magnitude of the S21, which gives us the mutual coupling. So let's say we say that at this 6 gigahertz. Okay. So 6 gigahertz, both the antennas give the VSWR less than 2, so it is kind of radiating properly. But here you can see that the red curve is slightly above. So red curve is denoting the case 2, which is basically for this system. So it is kind of expected because since we have connected the ground planes, we now have like coupling through that connected ground. So whether we can observe the energy distribution around the antenna and whether the energy distribution at this 6 gigahertz gives us a certain direction how the energy is coupled between the one antenna to the other. So for that, we have chosen some observation. We can choose various observation planes. So this is just one observation plane that I am showing here. And in one case, I excite the antenna by a simple Gaussian pulse that might be having some problems in the practical application, but just for the validation of concept purpose, we can use a simple Gaussian pulse over here and a modulated Gaussian pulse at the 6 gigahertz. So we could see that when we have the Gaussian pulse excitation, we can see certain kind of energy signatures and at this observation plane. And when we use the modulated Gaussian pulse, you can see how nicely you can observe that this antenna, the signature of this antenna and the energy signature of the other antenna, and how it is being coupled from one antenna to the other. And when we connect the ground plane, a clear increase in the coupled energy signature and also the region from how the energy is coupled. So for this structure, it might be obvious because we know from our knowledge, right? But the for any other maybe non-trivial or complicated antenna structure, this visualization can indeed identify that, okay, the basically the non-propagating energy between these multiple antennas is connected through this particular spatial path. So if we try to reduce the mutual coupling, we may try to find out the regions or we can identify the regions where we can put these kind of decoupling structures over. So this is another observation, and all of these we have tried to put in our paper in this representation of electromagnetic energy around antennas, current research and future direction. And it is available in IEEE Antennas and Propagation magazine in early access. So some of the, before going into some of the way ahead, we did have an invited article in this recently concluded RCRS conference at IIT BHU. So there we just had a few thoughts on the need for revisiting the classical accelerated charge model of the radiation to determine the non-propagating antenna energy analytically. And the main point, instead of going into the detailed maths, I will not bother you with all these maths, but the main point is that we can basically decouple the field around the antennas from this into this velocity and the acceleration terms. So the acceleration field basically contributes to the far zone radiated power and the propagating energy. But if we want to look into the non-propagating energy, it can have two distinct contributions. One contribution can come from the interaction between the velocity fields itself, and another component of the non-propagating energy can come from the interaction between the velocity field and the far field, and the acceleration field. So these things we tried to point out, and it was just open issues are identified, and we could conjecture that we can basically get into this prediction of this velocity field and acceleration field from the time domain infinitesimal dipole model also. So in the time domain IDM for this radiating current of the structure, one can basically visualize these small IDs or infinitesimal dipoles in terms of accelerated charges at various locations. So we can segregate analytically these two fields, velocity field and acceleration fields. So this was just the observation that we did and summarized over there. So with that, I will come to the conclusion of my talk, where the main points are once again summarized, that we need to look beyond the Q factors for electrically small antennas, and energy, because energy is a more general concept that is applicable for UWB or liquid wave antennas. And we can make use of certain useful algorithms like this FDTD based or IDM based algorithms to analyze the energy and visualize it beyond the time harmonic excitation. We can use it for pulse excited antennas. We can do it for transient states. And we have now introduced a new concept, pointing localized energy, which is distinct from the reactive energy. And the main feature is reactive energy does not have the spatial information, localized energy has it. And I also showed that localized energy concept is not simply a it's not simply a just fundamental research. It can have the application aspects or links to the gain enhancement and mutual coupling prediction between multiple antenna systems. And it can also have possible application in the near field energy transfer and wireless energy harvest. So with that, I thank you all for your attention, and I would like to take your questions. Thank you.
Thank you, Dr. Sharkar.
Yeah, thanks.
Yeah. So now the floor is open for question and answer. I request request all participants, please unmute your microphone and ask the questions directly to the speaker.
Sir, good evening, sir.
Yeah, good evening.
Sir, I have one question, sir. Why all the RF and micro engineers depends on the surface current distribution? Why not the other distributions like electric field, magnetic field, like that? Because in all your talk, you are discussing mainly on the surface currents.
Yeah, so I get your point. Like, it's a good question, but the point is that it is not that RF engineers don't look into the electric and magnetic fields. The point, surface current is emphasized upon here, and it is mostly from the antenna point of view, is that from the designer aspect. Suppose you want to design an antenna and you want to make it radiating along a specific direction. So there, what you have to ensure is how your shape of the antenna element, you want to change the shape. Now, when you are changing the shape, what exactly you are changing, what physical parameter you are changing, that is the current. So that is why we talk about the currents, be it a wire antenna, we talk about the linear current distribution. If it is a patch antenna, we talk about the surface current distribution. You can look into the electric current and magnetic current, all this kind of stuff. So that is the link between the fields and whatever input excitation you are putting into the system. So the current provides basically the link between that picture. So it is not that we are not interested in the fields, because when you try to say bring down the equivalent current model, say magnetic current model, then you have to look into the fields in the aperture, and from the aperture fields you get back the current. So I hope that answers your question.
Dr. Sarkar, shall I add a few points?
Yeah.
In this question, it is very relevant that normally students will ask. Can you hear me?
Yeah, I can hear.
Okay. So the thing is that once if you know the current, the surface current, the rest of the things, like electric field, magnetic field is a mapping. Current is the most important thing while you consider in antenna.
Yeah.
So once after the information of current, the surface current is there. Whatever the things you need, if you want to determine the electric field or magnetic field or radiated energy, whatever it is, that you can simply find out by using few calculations mathematically.
Yes.
So most of the antenna engineer will look into the highly complex thing that is in an antenna is to determine the current that is circulating in the surface of an antenna.
Yeah.
So most of the full wave analysis, MOM and FDTD, that is an important thing. That is why the antenna engineer is focusing on currents. Okay.
Yes.
That is most important.
Hello, can I ask a question?
Yeah.
Okay. Good evening, everyone. My name is Zumar, and I have joined this meeting from Pakistan. So greetings from my side.
Yeah.
Doctor, I have a question for you that in academics, we see that the research is, it's more for the publications rather than, the practical implementation. And, it is, nowadays, it's like you go for just publication. You don't care what is its implementation in real life. So can you please comment on this, that why is it so? Why don't we go for those things that can be utilized in daily life?
Yeah, well, so I think the point that you are trying to raise is mostly for the academic research point of view, and because I don't see that the research that is being done is not being done for the benefit of the humanity or stuff like that, because we design systems, we design circuits, and we design antennas, we design complex like algorithms to ultimately come up with a system that is useful for mankind. So the point is that from the academic research point of view, sometimes what I can say, my colleagues can also comment on that, sometimes the evaluation and all those things may pressurize certain academic people to focus on increasing the number of the publication. But definitely I agree with your point that the publication is not the only thing. Ultimate thing is whether the research is being applied for a certain application or certain building of the stuff. But again, there is another point that is to be noted, that some research can yield you practical application at the right after that, like it can form or shape into a particular product at that moment. But some of the research are needed so that it can lay foundation to building up systems maybe 10 years down the line. So what may seem to be a very theoretical exercise at the present moment can eventually be beneficial or can eventually come up as a very useful foundation for some applications 5 years or 10 years down the line. So we cannot always segregate between theoretical research and applied research. But yeah, I can get your point where you're coming from, and like I hope that I have addressed the issue.
Yeah, thank you.
Yeah.
Good evening, sir. One of my question is,
Yeah.
how much RF energy we can use for what are the efficiency and other things, sir?
Like you mean for the energy harvesting application or
Energy harvesting applications.
Yeah, so whatever, like I have not worked entirely on developing the RF energy harvesting circuit. Let me be clear about that. But I have seen the works of many of my colleagues in IIT Kanpur and also in other places. So the point is, so far, whatever the efficiency that they have obtained, like the input RF power to the DC efficiency, that is not yet of that level to maybe charge your wireless battery. But there are a few other companies that have built some kind of devices where you can use this near field wireless power transfer to charge up your, say, some device implanted or hearing aid and maybe some pacemaker. So these things have been done. So I am exactly not clear with the numbers, but generally, if you have to see that how much incident energy is there, whether it is some minus 20 dBm or minus 40 dBm, whatever is available in the near zone, and whether you can go rise up to something like 2 volts or 3 volts so that you can probably charge up for your specific application. So yeah, this is the kind of numbers or the range of numbers that you generally look for. So I hope that answers your question.
Thank you, sir.
Yeah.
Sir, I have one more question, sir.
Yeah.
Sir, if you take a simple microstrip patch antenna, sir, if you load some meta surface or FSS something stuff,
Yes.
sir, yeah, sir, will it give the maximum gain at the impedance matching point? Because I observed some shift in the frequency, sir. It won't give the gain at the same frequency where we get the impedance matching.
Yeah. So yeah, I think this is a very good question, and this is something that we all face, because when you model suppose you design the initial antenna at some frequency, and then you bring the impedance surface or the meta surface, whatever you close to the system. So definitely there will be some change in the frequency. So the general way how people approach it is to design it in situ, like whether put your FSS dimension as well as the antenna dimensions as variable and try to optimize it in the what should I say, like optimize it in a combined manner, like co-simulation. It's not exactly co-simulation, but in a combined manner you can change the dimension. So you have to have the design specs, like at what frequency you have to design. So it could be that when you want to have your exciter element at that particular frequency, isolated case, it can give you that response, but you have to see that whether you have to change the dimension accordingly when it is placed near the FSS. I hope you are getting my point. So your point is right, that it is not always possible that you design the patch at say 5 gigahertz and after that you put a superstate over it and it will give the impedance match at exact 5 gigahertz. It is not physically possible. You have to again change the dimension of the patch in presence of the FSS so that your impedance matches at the 5 gigahertz. So there is nothing wrong with that. It is a simple physical. Yeah.
Sir, my question is not that one, sir. Actually, my question is, after adjusting also, my question is a simple question. Is the impedance matching point exactly will give the maximum gain frequency?
Okay. Sorry. So yeah, I think you've also mentioned that point. I probably missed that one.
Yes.
Yeah. So it is not always true, because it will give you, suppose your antenna, what gives you the maximum gain enhancement. You have to first look into the mechanism. So let's say you talk about the Fabry-Perot kind of mechanism to explain your gain enhancement thing. So there you have to see that at that frequency, whether the spacing between your exciter element and the superstate is at the right condition. Like the spacing has to be a factor of the lambda. Maybe it can be lambda by 4, or maybe if you are using some other kind of thing, it can map into some other lens, other electrical lens. So you have to see that whether at that operation frequency, that criteria is satisfied. Or in some cases, people design this AMC or artificial magnetic conductor below your antenna. So there also, so it is not always true that where your maximum impedance matching or best impedance matching is there, that frequency might not conform to that wavelength mapping. So it might not give you the best possible gain. Best possible gain can occur at some other frequency point. So that is fine. Like I don't see any problem.
Thank you, sir.
Yeah, yeah.
You can also take 1 or 2 more questions. So if anyone has any more questions, so please feel free to ask.
Yeah, I think I have little bit time constraint till like 5 to 10 minutes I can stay. So
hello, sir. Sir,
yeah, please go ahead.
Yeah,
Yes.
yeah, sir. Can I ask a question once again?
Yeah.
Yeah. So my question is, do you, like when we simulate or when we fabricate the conformal antennas, we have seen that the radiation pattern of those antennas is distorted, and first of all, how to or our distort means it is disturbed. It's like if we compare the radiation pattern of a planar antenna, and then we design another antenna with same physical specs, and we just wrap it, or we we make it conformal, then then we'll observe that there's a difference between radiation pattern of both. So what are the different ways we can actually keep the radiation pattern intact while conforming the antenna?
Well, yeah, I think what you are saying is a bit of a challenge, and this exactly what sort of things that gives rise to a research problem. That for conformal thing, and when you are saying that it is conformal, I assume that you are basically going to wrap it, say body W-band application or something like that. You want to put it in your arm or put it in any other part of the body. So the various factors that actually come into the picture, like when you are conforming the antenna. So one of the ways that I can like quickly suggest, this can go on for long, but one of the ways is sometimes if the antenna is backed by equivalent PEC kind of layer or highly conducting layer, then the effect due to the body can be actually removed. And when you are talking about the distorting the shape itself, I'm afraid there will be some of the changes with respect to the planar antenna, equivalent planar antenna. So you have to simulate, or you have to simulate the antenna with the body itself. Like at the simulation stage, you got to have your phantom and the like most probable test scenario where you are going to implement the antenna, and whether you can wrap it on the simulation level itself, and then you can probably optimize your antenna shape. Because if you are simulating in a planar environment, planar kind of antenna situation, and then wrap it onto the body, then definitely it will not be same as that what we did in the planar environment. So I can suggest that way to probably reduce the distortion or reduce the changes between what you are predicting from the simulation and what you are going to get from the experiment. And again, I would like to point out one of the things here, that let's say we talk about antenna in a cell phone, where you have this PIFA kind of things. So when we talk about that, when we study the dipole or when we study the conventional monopole, we look for the omnidirectional radiation pattern and things like that. But when we use this PIFA near the cell phone, it is somehow like it will give you omnidirectional, but it will still be distorted. There will be still cross pole, and sometimes we have to define the matching condition by this -6 dB, like DSWR 3:1, all these kind of situation are there. So just distortion of the pattern from conventional or textbook kind of thing is not always the problem. We have to see that whether we are being able to get the data transfer or get the proper information exchange in that. Yeah.
All right. Thank you, sir.
Thank you, Dr. Sarkar, for such a nice and informative talk.
Thank you. It was my pleasure.
And I believe that many participants have benefited with your talk. And I would like to now request, without wasting much time, I know that you have to go somewhere.
Yeah.
So I would like to request Professor Abdullah. Professor Abdullah is once again, he is the chairman of the Antenna and Propagation Society, Kerala chapter, to say a few words and vote of thanks. Professor Abdullah, over to you.
Okay, thank you, Sugamal. And Dr. Sarkar, I have one more basic question also. I forgot to ask.
Yes.
And while calculating this localized energy,
yeah.
and in your previous initial plots, I observed localized energy versus various time. And what about when the distance, from the dipole itself? Normally, a near field is highly complex in nature. So you haven't shown any plot with respect to distance from the dipole. Is it
like
question?
I can probably go to the slide. Like I have shown, like if you see for example,
this I have seen the initial case. You have shown so many plots, here and all.
So these are some of the plots that I have used in the paper. So this can
my
be.
question is it possible in this analysis? Will you get it with respect to distance also from the?
Yes.
Okay,
Definitely. Yeah, that can also be another observation point, that with the distance in the linear kind of plot. Yeah, perfectly. Yeah, I think this is a good question.
Because it is highly non-linear, when you move from the structure to, so that is very important, because that will change the response.
Yes, definitely. And that can be.
Basically looking into where is that plot in different.
Okay. Yeah, so you can use like the way we defined the quantity. It can be evaluated for any simulation. Like if you want to go into a near field zone and you want to observe, so people are always welcome to do that. And maybe thanks for the suggestion. Maybe we can look into something like that.
Okay, thank you, Dr. Sarkar, and you have done a very wonderful job, and it was very informative and nice. The thing is that most of our students, they are not in India, they're not interested to do this hectic mathematics. They directly want to do their job just like a clerical person will do. They want to play with the software and get the result, fabricate it, measure it. And it is very difficult to get the students, like they want to most of the time involving in this mathematics, hectic mathematics and rigorous analysis.
Yes.
And you have done a very wonderful job. And definitely it should inspire our students and your students and those who are attending these seminars, because this types of work will give you the real picture and how an antenna work, and especially when we use the probe antennas and EMIMC antennas, when you want these types of analysis, very important while designing these sensors, especially EMIMC sensors and all. And you have done a better and a very good input to the students, those who attended this talk. And I am grateful to you for sparing your time with this APS today's evening. I also thanks the participants. Today we got participants from different states, not only from Kerala, from Andhra Pradesh, through my friends, Professor Ramana Reddy from JNTU, I think he left, and those who attended. I sincerely extend my gratitude as Chair, IPS Kerala chapter. And the last and not the least, and our Vice Chair, Dr. Sugamal, is the man behind, arranging all these seminars. And I thank you once again, Dr. Sarkar, and the other organizers, and Dr. Sukumal's research scholars, participants, and everybody. And you try tune the next week also, because we are doing this regularly now every week.
Yeah.
And it is benefited to the most of the research scholars, especially.
Yeah.
Okay. Thank you once again. Thank you all.
Thank you. It was my pleasure. Thank you,
Okay.
Dr. Abdullah.
Okay. Thanks.
Thank you. Thank you so much, Professor Abdullah.